Bismillahirrahmanirrahim. Assalamu alaikum. Dear student, my name is Sahib Noor and I will teach you Physics 2 in this semester. The subject code is GS131 and this subject is for BS Telecom and Electronics students of the second semester. This is a 3 credit hour course in which 2 credit is weighted to the theory part and 1 credit is for the lab work. The contact hours for the lab will be 3 hours, and this is our first lecture. Books for this course is recommended by the Board of Study, the committee, in which the textbook will be Fundamental of Physics by Walker, Holiday and Resnick. You can buy 8th edition or any latest edition available in your area. You can download this book from the Suit portal. The link is given as. Along with the textbook, a reference book is also being recommended by the Board of Study. The reference book is the University Physics, and which is written by Hooke D. Young, Roger A. Friedman, A. Lewis Ford, and you can buy 13 or 14 edition, which are the latest edition of this book. Similarly, you can download this book as well from the Suit portal, or you can type the given link into the Google search bar and you can download it by self. In this lecture, we will study topics from chapter number 15 of the textbook. The title name of the chapter is Oscillation. The main topics of this lecture are oscillation. We will define oscillation with some examples. Simple harmonic motion. This is a special type of oscillation and will be defined in terms of acceleration and force. Parameter of simple harmonic motion. We will discuss the necessary parameter in the simple harmonic motion. Velocity and acceleration of simple harmonic motion. We will start from the expression of the displacement and will derive the expressions for velocity and acceleration of simple harmonic motion. At the final part, we will study the Hooke's law and will explain certain parameters related to it. So let's start our first part, oscillation. We will define the oscillation along with the example. So the back and forth motion of an object about a fixed point is known as oscillation, or the object move back and forth repeatedly. The examples are when wind blows past a transmission line, the transmission line oscillates. It may oscillate up and down or left and right. The second example, when earthquakes occur, the building and many hanging object oscillates. In next example, a coin and a metal both oscillates when the coin drops into a metal plate. These were the example of the oscillation, but a special type of oscillation is simple harmonic motion, and this is because all the parameters related to this motion are well defined, and we will define simple harmonic motion in the upcoming slide. So what is simple harmonic motion? In this slide we are going to define simple harmonic motion in two ways. In terms of acceleration, it can be defined as the acceleration is directly proportional to the displacement but opposite in sign, or simply the motion in which the acceleration is proportional to the displacement but opposite in sign. These two parameters, the acceleration and the displacement, are related by a constant. So mathematically, a is directly proportional to x, where a represents the acceleration and the x represents the displacement, and the negative sign show that these two parameters are related, are acting in opposite direction. When we remove the proportionality sign, we will put a constant of the proportionality. Here the square of the angular frequency, omega square, is the constant of the proportionality. In terms of force, this can be defined as any vibrating system where the restoring force is proportional to the negative of the displacement, is in simple harmonic motion. The body which perform SHM, the body which perform simple harmonic motion, is known as the simple harmonic oscillator. So in terms of force, the restoring force will be proportional to the displacement and can be given as F is directly proportional to X, where F is the restoring force and X is the displacement. Or again, when we convert this proportionality sign into equality sign, we must insert a constant of proportionality. So K is known as constant of proportionality, or it may be called the elastic constant as well. So in this slide we define simple harmonic motion, which is a special type of oscillation. We define simple harmonic motion in terms of acceleration and in terms of force. You will see that the negative sign is sometimes called that the acceleration is toward the mean position, or in terms of force we said that the restoring force is always toward the mean position. In the current slide, we consider a simple harmonic oscillator, which is a mass attached to a spring, with consideration that mass of the spring is very small or negligible. When there is no force, then the object is in the equilibrium, that is, the object is at x is equal to 0, which is called the mean position. You will see at your screen, this position is known as the mean position. And when force is applied on this object to move it to the right of the mean position, then the restoring force will react instantaneously. After attaining the maximum displacement, which is xm, the object will move, the restoring force will tend to move the object at the mean position. But due to inertia, the object will not stop at x is equal to 0 and will move toward the left of the mean position. When the object attained the same maximum displacement on the left hand side, that is x is equal to minus xm, the direction of the motion will change again toward the right. So if we plot this displacement as a function of time, we will get the shape given in this figure. in which the time taken axis is horizontal and displacement is taken as vertically. When at t is equal to 0, the object start from the maximum displacement which was on the right hand side, and these vertically red lines indicate the maximum displacement on the right hand side. The upside of this figure is taken as positive, so this distance is the same as this one, and the negative displacement, which is the left hand side of the mean position, the maximum displacement is this red line, which is downward, vertically downward. So when t is equal to 0, the object was at xm, that is at the right side of the mean position. When time goes and after quarter time passed, the object comes, the displacement, the instantaneous displacement becomes 0. So at this point the displacement of the object is 0, and after half time period the object moves to the negative maximum displacement. So at this time the displacement is minus xm. You can see from the figure as well, and so on. After this, the object will move to the right hand side. First it will comes to the mean position and then will move to the maximum right side, and so on. So this mass attached spring system is a periodic system, and any motion that repeats itself in equal interval of time is known as a periodic motion. A sinusoidal motion is a function of time, which means that the sinusoidal motion depends upon time, and this motion is a sinusoidal motion, which is the displacement versus time plot of this oscillating system. Now, after discussing the various position of mass attached spring system, it is observed that the instantaneous displacement x of the simple harmonic oscillator can be written as x of t is equal to xm cos omega t plus phi, where x of t is known as the instantaneous displacement, which varies from 0 to xm or 0 to minus xm. This is the maximum displacement of the mean position, which is known as the amplitude, and then we need a sinusoidal function which varies from 0 to 1. The sinusoidal function, here we took cos function, you can take sine function as well, which is a sinusoidal function, and in the bracket the whole term is known as phase or argument. In next slide we will define these parameters separately. So parameters of simple harmonic motion: amplitude is the maximum displacement of the objects on the both sides of the mean position. It is denoted by xm, and the amplitude is always be a constant and positive. So this is the maximum displacement of the oscillating object about mean position. The instantaneous displacement is denoted by x of t and defined as the displacement of the oscillating object at any instant of time. It varies from 0 to xm, and the xm, which represent the amplitude, and xt, which represent the instantaneous displacement, have the same dimension, that is both representing the length dimensional quantity. The time period is defined as the time required for a single oscillation, or the time required for a single vibration. The time period is represented by capital T, and this is the specific time. The other parameters of simple harmonic motion, in which frequency is one of them. Frequency is defined as the number of oscillation in unit time, and can be given as f, which represent the frequency, is equal to n divided by t, where n is the number of oscillation and this t can be time period when n is equal to 1. So f is equal to 1 by t. The SI unit of frequency is hertz or second inverse. The next parameter is the phase. The phase is sometimes called the argument with a sinusoidal function, that this term omega t plus phi comes with a sinusoidal function, and the whole term is a unitless quantity, and it will give us a number which contain omega t plus phi and maybe some more terms. This will comes after a sinusoidal function, that is we can put it after sine or cos function. The next parameter is the angular frequency, which is also called the angular velocity. The angular frequency is denoted by omega and can be related with the time period of the object as omega is equal to 2 pi by t, where radian per second is the SI unit of the omega. At the right hand side of this slide, 3 figures are given in which displacement is plotted with respect to time, and here 2 waves of same frequency but different amplitude are plotted in this first part. Here the amplitude of the red wave is greater than the amplitude of the blue wave, but you can see that the displacement of both waves come to 0 at the same time, and then the amplitude, which is different but moves to the maximum displacement at the same time, and then come to 0, and then to the positive maximum displacement, and then 0. So in this case, in the first figure, the frequency of the 2 waves are the same, but the amplitude are the different. In the next figure, two motion are plotted with respect to time. In this figure, we observe that both the amplitude, so in this part you can see clearly the amplitude of 2 waves are the same, but the cycle are different. Cycle means that the red one complete its cycle earlier than the blue one. So there is a difference between the frequency of these 2 motions. And in the third figure, again the amplitude are the same, the frequency are the same, the 2 waves completes its cycle in the same time, but when one wave is started earlier than the other, so there may be a phase difference. So this phi is called the phase difference. In phase, the complete term is called phase, and the phi is known as the phase difference. So these are the parameters which are necessary to describe a simple harmonic motion. velocity and acceleration of simple harmonic motion. In this slide we will show that acceleration of the simple harmonic motion is directly proportional to the instantaneous displacement, or simply we are going to prove that for a simple harmonic motion acceleration is equal to minus omega square into t. So we will start from the definition of velocity, as velocity can be found by differentiating the instantaneous displacement, that is v of t is equal to dx by dt, that is derivative of position with respect to time. So we know that the instantaneous displacement of a simple harmonic oscillator can be written as this: x of t is equal to xm cos omega t plus phi. So if we differentiate it with respect to time, so if we put the value of this x over here and differentiate with respect to time, we will get minus xm omega sine omega t plus phi, and the positive quantity omega xm is known as the velocity amplitude, which will represent the maximum velocity, and this is a positive term. You can replace xm omega with vm and you can rewrite the expression as well. The acceleration of the object is time rate of change of instantaneous velocity. So if you put the value of velocity, this is the value of velocity over here, so you can get a is equal to minus omega square xm cos omega t. So if you clearly look this xm cos omega t, this was our initial equation, so you can replace xm cos omega t with the x of t. So finally we will get a is equal to minus omega square xt, and again the term omega square xm is called the acceleration amplitude, which is a positive quantity. So in this slide we prove that acceleration is equal to minus omega square into x, which is simply the definition of a simple harmonic motion. Hooke's law only valid within the elastic limit, which can be defined in terms of stress and strain. The stress is force per unit area and the unit of stress is Pascal. Due to stress, the length may be changed and the strain is defined as the change in length per unit original length. The strain is a unitless quantity. Here we define the Hooke's law in terms of restoring force. The restoring force of the elastic system is proportional to the displacement but opposite in sign. We can write F is equal to minus kx, which is the elastic force. Here k is the spring constant and the SI unit of spring constant is Newton per meter. Also from Newton's second law, force is given as F is equal to ma, and we proved earlier that acceleration a can be written as minus omega square into x. So if we put the value of acceleration over here, so the force will be minus omega square m into x, And if we compare this force with the elastic force, this one, so you will see that the left hand side of this equation is equal to the left hand side of this equation, so the right hand side will be equal as well, and we will simply get the value of k, which is equal to omega square into m, or you can find the omega will equal to square root k by m, where k is the spring constant and m is the mass of the object. You can also find the time period of this system, in which you can apply the formula which is earlier has been shown. T is equal to 2 pi by omega. When we put the value of omega, we will get T is equal to 2 pi under the root m by k. So from Hooke's law we can also derive the formula for time period for mass attached to a spring system, or the angular frequency in term of spring constant and mass term. What we have learned in our first lecture, let's sum them up. We study that what is oscillation. So from example we define oscillation, and also a special type of oscillation known as simple harmonic motion. We define simple harmonic motion in two ways, in term of acceleration and in term of force, and then we study the parameter or the characteristic related to this motion: amplitude, displacement, frequency, time period, phase difference, and so on. And at the last part of this lecture we study Hooke's law and derived some formulas for time period and angular frequency. In next lecture we will discuss the energy, potential energy, the kinetic energy, and the total energy of the simple harmonic oscillator, and we will also discuss the force and damped simple harmonic motion. I hope you will understand this lecture, and if you have any question you can contact me through my email, which is at your screen. Thanks and Allah Hafiz.